Hello, Chemistry 2330. Today we're going to continue our discussion of benzene and benzene derivatives. So this is Chapter 9, Part 1B. Okay, so as we continue on, we started with the idea that we have a resonance stability associated with making the benzene system more stable than just three double bonds kind of connected near each other. And so that further developed into the concept of aromaticity by Ulrich Huckel. And so we have some rules that you must follow to be a truly aromatic material. So the first thing to be aromatic is you must have a ring. So that is going to be the first requirement here. And so you must have a ring, and you must have one p orbital for each atom in that ring, okay? It can have one electron or two electrons or no electrons in it, but it must have a p orbital available to it. The ring must be planar or nearly planar such that all of those p orbitals can overlap and give a continuous or nearly continuous system. And you have to have a certain number of electrons, okay? You must have 2, 6, 10, 14, or 18 electrons. In most of our aromatic compounds we're going to start with a 6 electrons in our system. For example, benzene has 6 electrons in our pi system, okay? So thinking about that, that means benzene qualifies all of those criteria. It's cyclic, it's planar, it has one pi orbital for each of the carbons in that numbered ring. Each of those orbitals has a single pi electron in it, therefore it meets all of the requirements to make it an aromatic system. So, but do we have to have a carbon in the ring to make it that? No, we don't. And so because of that, we have what we can call heterocyclic compounds. Hetero meaning an atom other than carbon, and cyclic meaning it still has to be a ring to be aromatic, okay? So we have a lot of different ways to meet that criteria. So one of the first ones I'd like to talk about is this one is called pyridine. Pyridine is where we've taken one of the CHs out of benzene and replaced it with a nitrogen. Okay, so in this case right here, we still have a planar system, and notice there's a double bond to nitrogen here, meaning that is where the pi orbital is overlapped with the carbon next to it, and therefore we have 1, 2, 3, 4, 5, 6 electrons in there, and we meet the rule for 6 electrons, planar, pi orbitals, etc. We can also do that with this other compound here called pyrimidine, where now we've replaced 2 of them with nitrogens. Again, they're still double bonded to the carbons here. So that means that they are sp2 hybridized and have a lone pair available to it to make that double bond. And therefore, this also satisfies all the rules for becoming an aromatic compound. Okay. So let's discuss pyridine in a little more detail here to kind of prove to ourselves that it is truly that way. So first of all, the nitrogen atom is sp3 hybridized. It has this lone pair that is bonding to the carbon next to it to give us that double bond. And therefore, it does meet the requirements for having a total of 6 electrons above and below the plane of the benzene ring. Note that there is another lone pair on the nitrogen, but those are not sp, that is not the pi orbital, that is an sp2 hybridized orbital with unshared electrons in it, okay? Now, thing to note here is that pyridine has a resonance energy of 130 kilojoules per mole. Remember, benzene was 151 kilojoules per mole. Okay, so it's not as stable there, and that's possibly due because the nitrogen here contributes a little less energy to the system. So it's a little bit less than benzene, but it's still stabilized from just having isolated double bonds. Okay, so in all of the aromatic systems we talked about so far, those were 6-membered rings. But it's possible to do this without a 6-membered ring. And so let's go into the concept of having aromaticity, but having less than 6 members in your ring, but still meet all the other requirements. So the first one I'd like to talk about is called furan. And so furan, if I draw it out here, we have an oxygen here and a double bond. And then so we have 2 lone pairs on that oxygen here. So when we think about this, you're going, oh, well, how does that actually contribute to our system? Well, we have one electron here, one electron here, one electron here, one electron here, and then we have two lone pairs on this system. So if these two lone pairs were in a p orbital and these two lone pairs were in an sp2 hybridized orbital sticking out from them, then these two orbitals, these two electrons here, could contribute to the 6 electrons required to the system. So that's what actually happens. We end up with a total of 6 electrons to make our aromatic ring. We still have a ring, it's still flat. And then we have the last two electron pairs in an sp2 hybridized orbital to give us our total octet for each of the molecules. So furan here is a perfectly aromatic system, okay? But it only has a 5-membered ring, okay? We can do that again with a nitrogen as well. So we'd expect there to be a lone pair on the nitrogen, but nitrogen's gonna have 3 bonds, so it actually has a hydrogen bonded as well. That makes these electrons in a 2p orbital, along with all of these electrons in the 2p orbital, giving us a total of 6 electrons to give us our aromatic ring. And even though we have, again, 5 atoms in the ring, we still have meet all of our goals of planar, cyclic, and 6 electrons in p orbitals. Okay, so how can we use this to our advantage? Well, there's a lot of organic compounds and a lot of biologically active compounds that use the same theory that help us with it. So if we look at this compound here, indole, we have our regular benzene ring that we would normally have, but then we also have a 5-membered ring pyrrole that is fused to it. And so when we have those together, we call that indole, okay? Now, where is this used in the body? Well, it's the core molecule of serotonin, which is a neurotransmitter in both the brain and in the bowel of the human body. So just by derivatizing with the alcohol and this group right here, we have a very active and used in the human body species. Another way to do it is if we took indole and instead of just having this one substitution with nitrogen, we actually do 3 more nitrogens on the system here, we can get to this purine here, which is also an aromatic compound, and it's used in the body for adenine. Adenine is used in a bunch of different processes, including DNA. Okay, so let's get into some of the nomenclature here. So obviously, if it's by itself, it's benzene. It's not cyclohexatriene. We have a common name for it is benzene right here. And because it reacts differently, it doesn't act as cyclohexatriene, okay? So there are some common names for it, and there are some regular systematic names for it. Anytime you have alkyl benzenes that are monosubstituted, they tend to be named for the alkyl chain if they're long, so we have ethylbenzene or propylbenzene, etc. But when we have just the methyl group, that's a common enough material that we use that we have a special name for it. We call that toluene. Okay, this is a common solvent. You can go down to Home Depot or Lowe's and buy some and use it for cleaning up parts in your garage here. Another common name that we have is called styrene, and that's where we have this vinyl group on here. It could be technically called vinyl benzene, but styrene, you might know from polymer chemistry, is polystyrene. This is the molecule that polystyrene is made out of, and so it has a special name as well. Okay, if we have an OH group on there, we now can call it phenol. So if you can think about it, it's phenyl alcohol is phenol in there. If we have a nitrogen here, notice it's outside the ring, it's not inside the ring, so it's not pyridine. So we call that aniline. And these two are fairly easy because this is an aldehyde and this is a carboxylic acid. So we have benzaldehyde and benzoic acid. And then here, if we have this methyl ether right here, that's called anisole, okay? And so if we have any of these groups in our system, those common names become the parent for any other naming of an organic compound we have, okay? So let's continue on with nomenclature. So if you have benzene itself, it's called benzene, but if you have something bonded to where one of the hydrogens is right here, we now call it the phenyl group, okay? So that's the phenyl substituent on some other chain. Okay, so if we look here, we have a butene right here. And so we have 1, 2, 3, 4 butene. So it's 4 is butene. And so we have the double bond start on the 2. So it's 2 butene. And we have a phenyl group substituted on that 2 carbon as well. So we have 2 phenyl, 2 butene. And then if we look at the priority here, this half of the molecule, this group takes priority. This half of the molecule, this takes priority. So these are on the same side. So that gives us our Z denotation. So we have Z, 2 phenyl, 2 butene as our common name, as our IUPAC name for that. Okay, now, one of the common names for our materials here is the toluene right here. If we take one of these hydrogens off and bond it to something here, that now becomes the benzyl substitution group, okay? So if we have, for example, put a chlorine here, we would have benzyl chloride. Or if we put an amine here, we'd have benzyl amine. So, and we'll learn about amines in the next chapter. Okay, so for example, another way to name this thing here is this would be ethanol. And so since this is being named for this alcohol here, this is the 1 carbon and this is the 2 carbon. And so our name would end up being 2-phenyl ethanol. Okay, so nomenclature follows a lot of the same rules we have, but we have to start thinking about the benzene as a substituent or the benzyl group as a substituent. Okay, so that's if we had 1 substitution on benzene. What if we start having 2 substitutions on benzene? Okay, so when we have 2 substitutions on benzene, we have to start thinking about what position they're in. So in the simplest case right here, we would have a methyl group, which means we have to name it as toluene, because that's the common name. But we have it where we have it in, so that makes this the 1 position. And so then this would be the 2 position. So this would be our 1,2 substituted toluene. Or we could call it, it also has a common name called ortho. Ortho means 1, 2, or right next to each other. Okay, so if they were substituted in the 1,3 configuration, so in this case we have nitrogen here on the side here, so we have to name it aniline. And so that becomes our 1 position, our 2 position, and our 3 position. So this is now a 1,3 substituted aniline, or meta-aniline right here. And then in this case right here, we have a substitution that's para. We have toluene right here because of the methyl group here, names it there. And we have the 1, 2, 3, 4 position here, which makes it 4-bromotoluene, or we would call that 1,4 substitution is called para substitution. So that's what this little P stands for, is para. This little M stands for meta, and if we have ortho, it'd be a little teeny O. It would be ortho substituting. Okay, now, if we don't have a name or we have multiple things that would make it a name, for example, we have 2 methyl groups here. So 2 methyl groups can no longer be toluene because then it'd be methyl toluene. Which one would take precedent? We don't know. So what we're going to name it as, well, 1 group is 1. We're going to do our lowest number, so that'd be 2 and 3. So we have 1,3-dimethyl benzene. Well, it turns out 2 methyl groups on a benzene ring does have a common name, and we call that xylene. So we call this meta-xylene because it's 1,3. You could also have 1,2 or 1,4, and they would, of course, be orthoxylene or paraxylene. Okay. Now, if you have a molecule that doesn't have a special name to it, like this right here, we're going to name it like we name other compounds that have substituents. We're going to figure out the smallest number possible, and in this case, we can go 1 to 4 around the system, 1, 2, 3, 4. And so that would be the smallest derivative, the smallest number between them. But now we go in alphabetical order. So chloro group comes before ethyl group. Therefore, we have 1-chloro, 4-ethyl benzene, or in this case, because it's a 1,4 substitution, we can also call it para-chloroethylbenzene. Okay, so we're using all of those same nomenclatures we have, but we're adding something where if it's a 1,2, we have the ortho configuration. If it's 1,3, we have the meta configuration. And if it's 1,4, we have the para configuration. Okay. So what if we have more than 2 substituents? Okay. So when we have more than 2 substituents, we start where we started before, where if it has a common name, we start with that common name. So in the case of this first compound here, we have toluene because we have this methyl group here. And then we're going to name it, we're going to number it with the smallest number possible. So if we numbered right here clockwise, we'd go to 1 to 4. If we named it counterclockwise, however, we'd end up with 4 and 6. So we aren't going to do this. We're going to only name it clockwise. And so then when we do, we name it clockwise with the lowest number, and then we alphabetize. So in this case, the chloro comes before the nitro group. So we have 4-chloro, 2-nitro, toluene. Okay. So when we can't go by number, we go by the alphabetization. Okay. So in this case right here, we have OH. OH tells us it's a phenol. That's one of our special names. And we can number it either way, clockwise or counterclockwise, because we'll end up with a 2, a 4, and a 6 position. Therefore, we get 2,4,6 tribromophenol. Again, if we had another substituent on here that was less than B, it would be before this. If it was higher than B, it would be after this. Because remember, the prefix does not count in alphabetization. Okay? So if we look at this last compound here, we have no special group here. So it's not toluene or anything else. So what we do is we go by the smallest number possible, okay? So the smallest number possible is going to be 1, 2, 4. If we named it the other way, it'd be 1, 4, 6. So our smallest direction is going to be going counterclockwise in this case. And then we alphabetize. So bromine would come first, so it's 2-bromo. And then the ethyl group would come next alphabetically, so it'd be 1-ethyl, and then the nitro would come last, 4-nitrobenzene. Okay, so that's just like a lot of our other rules. We're going to name it by the lowest number first and then alphabetize. Okay. So, and that brings us up to some of more of our polyaromatic systems right here. They have special names. 2 fused benzene rings is naphthalene. If you have 2 benzene rings that are not fused, that's biphenyl for 2 phenyl rings. When we have 3 fused rings, it's anthracene. This is phenanthrene because it's similar to anthracene, but phenanthrene. And when we have this group of 4 right here, this is called pyrene. And therefore, if we have a benzene fused to it, it's benzopyrene. Okay, so that brings us to the end of chapter 9-1, part B, Nomenclature and Aromaticity.